India's first great mathematical gift lay in the world of number. Like the Chinese, the Indians had discovered the mathematical benefits of the decimal place value system and were using it by the middle of the 3rd century AD. It's been suggested that the Indians learned the system from Chinese merchants travelling through India with their counting rods. Or they may well just have stumbled across it themselves. It's all such a long time ago that it's shrouded in mystery. We may never know how the Indians came up with their number system, but we do know that they refined and perfected it, creating the ancestors for the 9 numerals we use across the world today. Many rank the Indian system of counting as one of the greatest intellectual innovations of all time, developing into the closest thing we could call a universal language. But there was one number missing, and it was the Indians who would introduce it to the world. The earliest known recording of this new number dates from the 9th century, though it was probably in practical use for centuries before. This strange new numeral is engraved on the wall of a small temple in the fort of Gwalior in central India.
So here we are, in one of the true holy sites of the mathematical world. And what I'm looking for is in this inscription written on the wall. Up here are some numbers, and here's the new number. It's 0.
It's astonishing to think that before the Indians invented it, there was no number 0. To the ancient Greeks, it simply hadn't existed. To the Egyptians, Mesopotamians, and as we've seen, the Chinese, 0 had been in use, but as a placeholder, an empty space to show a 0 inside a number. The Indians transformed 0 from a mere placeholder into a number that made sense in its own right, a number for calculation, for investigation. This brilliant conceptual leap would revolutionise mathematics. Now, with just 10 digits, 0 to 9, it was suddenly possible to capture astronomically large numbers in an incredibly efficient way. But why did the Indians make this imaginative leap? Well, we'll never know for sure, but it's possible that the idea and symbol that the Indians used for 0 came from calculations they did with stones in the sand. When stones were removed from the calculation, a small round hole was left in its place, representing the movement from something to nothing. But perhaps there's also a cultural reason for the invention of 0. For the ancient Indians, the concepts of nothingness and eternity lay at the very heart of their belief system. In the religions of India, the universe was born out of nothingness, and nothingness is the ultimate goal of humanity. So it's perhaps not surprising that a culture that so enthusiastically embraced the void should be happy with the notion of 0. The Indians even used the word for the philosophical idea of the void, shunya, to represent the new mathematical term 0. In the 7th century, the brilliant Indian mathematician Brahmagupta proved some of the essential properties of 0. Brahmagupta's rules about calculating with 0 are taught in schools all over the world to this day. 1 plus 0 equals 1. 1 minus 0 equals 1. 1 times 0 is equal to 0.
But Brahmagupta came a cropper when he tried to do 1 divided by 0. After all, what number times 0 equals 1? It would require a new mathematical concept, that of infinity, to make sense of dividing by 0. And the breakthrough was made by a 12th century Indian mathematician called Bhaskara II. And it works like this. If I take a fruit and I divide it into halves, I get 2 pieces. So 1 divided by half is 2. If I divide it into thirds, I get 3 pieces. So when I divide it into smaller and smaller fractions, I get more and more pieces. So ultimately, when I divide by a piece which is of 0 size, I'll have infinitely many pieces. So for Bhaskara, 1 divided by 0 is infinity.
But the Indians were to go further in their calculations with 0. For example, if you take 3 from 3 and get 0, what happens when you take 4 from 3? It looks like you have nothing. But the Indians recognised that this was a new sort of nothing, negative numbers. The Indians called them debts because they were perfect for solving equations like, if I have 3 batches of material and take 4 away, how many have I left?
This may seem odd and impractical, but that was the beauty of Indian mathematics. Their ability to come up with negative numbers and 0 was because they thought of numbers as abstract entities. They weren't just for counting and measuring pieces of cloth. They had a life of their own, floating free of the real world. This led to an explosion of mathematical ideas.
The Indians' abstract approach to mathematics soon revealed a new side to the problem of how to solve quadratic equations. That is, equations including numbers to the power of 2. Brahmagupta's understanding of negative numbers allowed him to see that quadratic equations always have 2 solutions, one of which could be negative.
Brahmagupta went even further, solving quadratic equations with 2 unknowns, a question which wouldn't be considered in the West until 1657, when the French mathematician Fermat challenged his colleagues with the same problem. Little did he know that they'd been beaten to a solution by Brahmagupta 1,000 years earlier.
Brahmagupta was beginning to find abstract ways of solving equations. But astonishingly, he was also developing a new mathematical language to express that abstraction. Brahmagupta was experimenting with ways of writing his equations down, using the initials of the names of different colours to represent unknowns in his equations.
A new mathematical language was coming to life, which would ultimately lead to the X's and Y's which fill today's mathematical journals.
But it wasn't just new notation that was being developed. Indian mathematicians were responsible for making fundamental new discoveries in the theory of trigonometry. The power of trigonometry is that it acts like a dictionary, translating geometry into numbers and back. Although first developed by the ancient Greeks, it was in the hands of the Indian mathematicians that the subject truly flourished. At its heart lies the study of right-angled triangles.
In trigonometry, you can use this angle here to find the ratios of the opposite side to the longest side. There's a function called the sine function, which when you input the angle, outputs the ratio. So for example, in this triangle, the angle is about 30 degrees. So the output of the sine function is a ratio of 1 to 2, telling me that this side is half the length of the longest side.
The sine function enables you to calculate distances when you're not able to make an accurate measurement. To this day, it's used in architecture and engineering. The Indians used it to survey the land around them, navigate the seas, and ultimately chart the depths of space itself. It was central to the work of observatories like this one in Delhi, where astronomers would study the stars.
The Indian astronomers could use trigonometry to work out the relative distance between the Earth and the Moon and the Earth and the Sun. You can only make the calculation when the Moon is half full, because that's when it's directly opposite the Sun. So the Sun, Moon and Earth create a right-angled triangle.
Now the Indians could measure that the angle between the Sun and the observatory was 1/7 of a degree. The sine function of 1/7 of a degree gives me the ratio of 400 to 1.
This means that the Sun is 400 times further from the Earth than the Moon is. So, using trigonometry, the Indian mathematicians could explore the solar system without ever having to leave the surface of the Earth.
The ancient Greeks had been the first to explore the sine function, listing precise values for some angles. But they couldn't calculate the sines of every angle. The Indians were to go much further, setting themselves a mammoth task. The search was on to find a way to calculate the sine function of any angle you might be given. The breakthrough in the search for the sine function of every angle will be made here in Kerala in South India. In the 15th century, this part of the country became home to one of the most brilliant schools of mathematicians to have ever worked. Their leader was called Madhava, and he was to make some extraordinary mathematical discoveries.
The key to Madhava's success was the concept of the infinite. Madhava discovered that you could add up infinitely many things with dramatic effects. Previous cultures had been nervous of these infinite sums, but Madhava was happy to play with them. For example, here's how 1 can be made up by adding infinitely many fractions.
I'm heading from 0 to 1 on my boat, but I can split my journey up into infinitely many fractions. So I can get to a half. Then I can sail on a quarter, then an eighth, then a 16th, and so on. The smaller the fractions I move, the nearer to 1 I get. But I'll only get there once I've added up infinitely many fractions.
Now, physically and philosophically, it seems rather a challenge to add up infinitely many things. But that's the power of mathematics, to make sense of the impossible. By producing a language to articulate and manipulate the infinite, you can prove that after infinitely many steps, you'll reach your destination.
Such infinite sums are called infinite series, and Madhava was doing a lot of research into the connections between these series and trigonometry. First, he realised that he could use the same principle of adding up infinitely many fractions to capture one of the most important numbers in mathematics, pi. Pi is the ratio of the circle's circumference to its diameter. It's a number that appears in all sorts of mathematics, but is especially useful for engineers because any measurements involving curves soon require pi. So for centuries, mathematicians searched for a precise value for pi.
It was in 6th century India that the mathematician Aryabhata gave a very accurate approximation for pi, namely 3.1416. He went on to use this to make a measurement of the circumference of the Earth, and he got it as 24,835 miles, which amazingly is only 70 miles away from its true value.
But it was in Kerala in the 15th century that Madhava realised he could use infinity to get an exact formula for pi. By successively adding and subtracting different fractions, Madhava could hone in on an exact formula for pi. First, he moved 4 steps up the number line. That took him way past pi. So next, he took 4/3 of a step, or 1 1/3 steps, back. Now he'd come too far the other way. So he headed forward 4/5 of a step. Each time he alternated between 4 divided by the next odd number. 4/7, 4/9, 4/11, and so on. He zigzagged up and down the number line, getting closer and closer to pi. He discovered that if you went through all the odd numbers, infinitely many of them, you would hit pi exactly.
I was taught at university that this formula for pi was discovered by the 17th century German mathematician Leibniz. But amazingly, it was actually discovered here in Kerala 2 centuries earlier by Madhava. He went on to use the same sort of mathematics to get infinite series expressions for the sine formula in trigonometry. And the wonderful thing is that you can use these formulas now to calculate the sine of any angle to any degree of accuracy.
It seems incredible that the Indians made these discoveries centuries before Western mathematicians. And it says a lot about our attitude in the West to non-Western cultures that we've nearly always claimed their discoveries as our own.
What is clear is the West has been very slow to give due credit to the major breakthroughs made in non-Western mathematics. Madhava wasn't the only mathematician to suffer this way. As the West came into contact more and more with the East during the 18th and 19th centuries, there was a widespread dismissal and denigration of the cultures they were colonising. The natives, it was assumed, couldn't have anything of intellectual worth to offer the West. It's only now, at the beginning of the 21st century, that history is being rewritten.
But Eastern mathematics was to have a major impact in Europe, thanks to the development of one of the major powers of the medieval world.